Yeah, so hello everybody. I'm Steffen Limmer from the Honda Research Institute Europe. And in the following, I want to talk about the results of an internship project of Takahiro Ishihara from the Taitech University in Tokyo, who investigated the optimization of hyperparameters of a MILP solver to speed up electric vehicle charging control. As you know, there's an increasing number of electric vehicles. Today, the charging of EVs is usually done uncontrolled, but there's an increasing interest in controlled or smart charging of EVs because this can help to solve issues with the distribution grid and can make EV charging more cost efficient. And in the literature, there are different approaches for EV charging control, where the advanced approaches usually plan multiple time steps ahead. So that means they plan the charging powers of the plugged-in EVs for multiple time steps in the future with respect to a certain objective, like minimizing the costs and under certain constraints, where one constraint is usually that the charging demands of the EVs are fulfilled. And yeah, this planning is an optimization problem, and this is commonly solved with help of linear programming or mixed integer linear programming. Linear programming is an exact approach, so it finds the global optimum in a finite time, and it is very efficient. But nevertheless, the runtime can present a serious issue because in practice, the scheduler or controller has to react fast. The time to solve a given linear programming problem depends on the used solver. There are different commercial solvers available like Cplex or Ruby, but also non-commercial solvers like LPsolve and SCIP. And the solving time does not only depend on the used solver, but also on the setting of the parameters of the solver. For example, SCIP has over 1,600 parameters. And the default setting of the solver parameters is usually in a way that a good average performance is achieved on heterogeneous problem instances, but restricted to a certain problem class, the default settings are not necessarily optimal. And so tuning the parameters of the used MILP solver is a promising way to speed up the scaling for the EV charging control. The question is how to tune the parameters. Tuning the parameters manually or with a simple approach like grid or random search is not very efficient. One could use a general black box optimizer like CMAS, but there are also hyperparameter tuning approaches which are specialized for this task, and that's what we investigated. More precisely, we evaluated the two popular hyperparameter tuning approaches, irace and SMAC, for tuning the parameters of the SCIP solver on 4 variants of the EV charging scaling problem in order to investigate the following questions. First, to which degree can the charging scaling be accelerated by tuning the solver parameters? Second, which tool is better suited for this task, irace or SMAC? And based on the optimization results, we investigate which solver parameters are the most important ones. And yeah, that's what I want to talk about in the following. And first, I want to provide some background information to hyperparameter optimization. I will then say some words to this SCIP solver. Then I will discuss the experiments and their results, and finally provide a small conclusion and summary. Yeah, so first, hyperparameter optimization. Here you can see the general concept. In order to tune the parameters of an algorithm A with a certain hyperparameter tuning tool or optimizer, one has to provide a set of problem instances for the algorithm, the so-called training instances. Furthermore, a specification of the parameter space has to be provided and a budget, for example, a time limit. The parameter tuning tool then optimizes the parameter of the algorithm with respect to a certain fitness, or precisely with respect to the average fitness on the training set. And in order to evaluate a certain parameter setting on a training instance, it calls the algorithm. More precisely, usually some kind of wrapper has to be provided, which calls the algorithm and computes the actual fitness, for example, measures the runtime. And when the budget is reached, the optimizer outputs a hopefully optimal parameter setting. And since we want this parameter setting to perform well also on unseen problem instances, not only on the training instances, the resulting parameters are then usually evaluated on a set of test programs. And there are different tools available which can be used here for the parameter optimization. And as already mentioned, we use the two popular tools, irace and SMAC. Irace works as follows. It starts with a set of random parameter configurations. These configurations are then evaluated on a number of random training instances. Then the statistical test is performed to test whether some of the parameter configurations performed significantly worse than others. If this is the case, the worst configurations are removed. And then the remaining configurations are evaluated on a further number of random training instances and so on under a certain minimum number of instances or parameter configurations remain the so-called elite configurations. And this process here is also called racing. And then new configurations are generated by randomly sampling around the elite configurations, and the new configurations together with the elite configurations then go again in this racing and so on until the budget is reached. And the variance of the sampling here decreases from iteration to iteration so that the search focuses more and more on a promising region of the search space. And the second tool we used, SMAC, employs Bayesian optimization for the optimization of the parameters. In contrast to the original Bayesian optimization, it does not use a Kriging model as surrogate model. Instead, it uses a random forest because random forest can better deal with discrete inputs. And in each iteration, it does not select only one new point of the search space, but multiple new points, so multiple new parameter configurations. And in order to compare multiple parameter configurations, it uses an approach called intensification, which works quite similar to this racing approach of irace. And we tuned the parameters of SCIP. SCIP is one of the fastest non-commercial mixed integer linear programming solvers, if not the fastest. Nevertheless, solving a given problem can take a long time. That's why it's possible to specify a time limit for the solving process. And if no exact solution is found within the time limit, SCIP returns the best solution found so far, together with an optimality gap, which is an upper bound for the percentage gap to the global optimum. And as already mentioned, SCIP has a lot of parameters, more than 1,600 parameters. And in addition to the default setting of the parameters, it provides 3 further predefined parameter settings called fast, aggressive, and off. And in experiments, we tuned the parameters of SCIP in order to speed up the EV charging scheduling. The EV charging scheduling problem can be formulated in different ways with different objectives and different constraints. And we assume a basic version where a charging provider can buy and sell energy for real-time electricity prices, which fluctuate over time. And the actual problem is to optimize charging plans for N plugged-in EVs with the objective to minimize the electricity costs under the constraints that the charging demands of the plugged-in EVs are fulfilled, and that in each scaling interval, lower and upper limits for the total charging power are satisfied. For example, to avoid transformer overloads or high peak demand charges. And in the experiments, we consider 4 variants of this problem: 2 with continuous power modulation, 2 with discrete modulation. In the first variant, EVs can only charge, not discharge, and the power can be modulated continuously between 0 and the maximum charging power of the EV. And the second variant, EVs can also discharge. In the third variant, EVs can only charge and the power can be only set to 0 or the maximum charging power of the EV. So it's basically an on-off scaling. And in the last variant, EVs can also discharge and the charging power can be set to maximum discharging, 0, and maximum charging. The first 2 variants are purely continuous, while the second 2 variants contain integer variables. That's why the first 2 variants are easier to solve than the second 2. And the hardest variant is the last one, with charging, discharging, and discrete modulation. And the experiments, we used the following setup. We tuned the parameters of SCIP. For each problem variant, we randomly generated 100 training problems and 60 test problems with different charging demands and different numbers of EVs and so on. And since the different problem variants are differently hard to solve, we picked a number of EVs from different ranges for the different problem variants. For the easier variants, we use higher ranges than for the harder variants. And for the continuous variants, we tune 316 parameters of SCIP. For the discrete variants, we tune 420 parameters. The reason why we tune different parameters here is that some parameters have no influence on solving purely continuous problems. And yeah, since it can take, for some problem instances, it can take a very long time to solve them exactly, we set a time limit of 40 seconds for each solving process and use the optimality gap as penalty in the fitness function. More precisely, the fitness for solving a given problem instance is the normalized solving time plus this penalty in the optimality gap. For instances which can be solved exactly within 40 seconds, the gap is 0 and the fitness is between 0 and 1. And for instances which can be not solved within the 40 seconds, the fitness is between 1 and 2. And for the parameter tuning, we use irace and SMAC with default settings. And as baseline, we also consider random search on 10 randomly selected training instances. And for each parameter tuning approach and each problem variant, we executed 40 trials with a budget of 3,000 evaluations per trial. And here you can see the results of the experiments. You can see here for the 4 problem variants, the average progress of the average fitness on the test set over the number of evaluations for the 3 parameter tuning approaches. The dashed line indicates the fitness with the default parameter setting of SCIP. And yeah, we can see that at the beginning of the optimization process, SMAC outperforms the other 2 approaches, but with exception of the charge-discharge continuous variant, irace converges to better final results. Furthermore, one can see that all 3 approaches find better settings than the default setting of the parameters. And on all 4 problem variants, irace and SMAC outperform random search. You can again see the average progress of the fitness, but here not over the number of evaluations, but over time. You will see that random search is more time consuming than irace. The reason is that random search evaluates a lot of poor parameter configurations, resulting in high solving times. And one can see that SMAC is even more time consuming. The reason is probably that with this high number of parameters, the training and the evaluation of the surrogate model inside SMAC is rather time consuming. Yeah, so all 3 approaches find better settings than the default settings. What does this now mean exactly for the solving times? You can first see for the 4 problem variants, the mean solving times on the test set with the 4 predefined parameter settings of SCIP. You can see that there's actually no big difference between the different settings. And here you can see the mean solving times with the parameters optimized with irace, SMAC, and random search, together with the average percentage improvement compared to the best predefined setting. And yeah, one can see that the improvement varies over the problem variants. For the charge discrete variant, an improvement of about 50% is achieved, so a speed up of about 2. While for the charge discharge discrete case, an improvement of only 8.5% is achieved, but nevertheless, still a notable improvement. And one can see that there's only 1 problem variant for which SMAC yields better results than irace, but on this variant, the difference between irace and SMAC is statistically not significant, while for the other problem variants, the differences between irace and SMAC are statistically significant. So we can say that irace yields statistically significant better results than SMAC for the given problem. Now, the question is, can we gain some useful information from the optimization results? And That's what we investigated in further experiments. More precisely, we investigated which of the solver parameters are the most important ones. And we did this based on the optimization results on the following assumption. Parameters for which their corresponding values in the optimization results have a high variance are probably not important. So their settings should have no big influence on the performance. And so we identify the most important parameters in the following way. First, we test for each parameter with the chi-square test whether its corresponding value in the optimization results is uniformly distributed. Then, based on the results of the chi-square tests, we divide the parameters into groups. Parameters with a p-value less equal 5% are treated as important, and their corresponding value, their values are set to the corresponding mode or mean values in the optimization results. And parameters with a p-value higher than 5% are treated as unimportant, and their values are set to the corresponding default values. Then we evaluate the resulting parameter setting on the test set, and then we iteratively remove the parameter with the highest p-value from the group of important parameters and add it to the group of unimportant parameters, evaluate the resulting parameter setting, and so on until the performance significantly decreases. And here you can see for the 4 problem variants, the resulting important parameters and their settings, and the resulting average fitness on the test set. So the fitness when the important parameters are set as listed here and all other parameters are left to default. And for comparison, you can see here the mean fitness achieved with irace and SMAC optimizations. And yeah, one can see that only 1 to 4 parameters remained in the group of important parameters, and the resulting fitness is better than the mean fitness achieved with irace and SMAC optimizations. So one can say, although we considered a high number of parameters in the optimizations, only a small number of parameters is actually worth the tune. But unfortunately, as you can see, which parameters these are and their optimal settings depend on the problem variant, so we cannot derive some more general guidelines which parameters to tune. Okay, so as conclusion, let's come back to the initial questions. The first question was to which degree the charging scheduling can be accelerated with help of the solver parameter tuning. We have seen that this depends on the problem variant. For the variants where only charging is possible, an average time improvement or runtime improvement of up to 66% was achieved. For the variants where also discharging is possible, the improvements were less, but still up to 18%. So we can say in both cases, notable improvement in the runtime or speed up was achieved. Then the second question was which tool is better suited for the given problem, irace or SMAC. Here we can clearly say irace. Irace yielded statistically significant better results than SMAC. And additionally, it is less time consuming than SMAC. And the third question was which solver parameters are the most important ones. And yeah, we found that only 1 to 4 parameters are actually worth the tune. But as you have seen, which parameters these are and their optimal settings depend on the problem variant. As future work, we plan to also tune the parameters of irace and SMAC. In the experiments here, we use default settings for irace and SMAC, but irace and SMAC have itself parameters which influence the optimization process. And by tuning these parameters, maybe even better results can be achieved. Yeah, and this brings me to the end. Thank you for your attention.